There is one moment in the entire 49-year history of the Voyager 1 mission that nobody who has ever heard about it has been able to fully set down afterward. Not the volcanic eruptions on Io, not the rings of Saturn photographed in detail for the first time, not the crossing of the heliopause into interstellar space. One moment on February 14th, 1990, when the engineers at NASA's Jet Propulsion Laboratory sent a command to a spacecraft that was already 4 billion miles from Earth and told it to do something it had never been designed to do and would never do again. They told it to turn around, not physically. The spacecraft continued on its trajectory without interruption, but its camera platform, the instrument array that had been pointed outward at the planets and moons and rings of the outer solar system for over a decade, was commanded to rotate, to look back, to point its cameras at the direction from which it had come. And in a sequence of 60 frames taken over the course of 3 hours, Voyager 1 photographed the solar system it was leaving. Every planet it could see from that distance. And in one of those frames, a single frame among 60 in a band of scattered sunlight that cuts diagonally across the image, there's a pale blue dot, barely a pixel, almost invisible, the planet Earth, 4 billion miles away. The only home humanity has ever known, captured in a photograph that Carl Sagan spent years fighting to have taken, and that, when he finally saw it, produced the most important thing any scientist has ever said about the human species and its place in the universe. And then the cameras were turned off forever. To understand why that moment matters as much as it does, and why the discoveries that Voyager 1 has made since it left the solar system entirely cannot be separated from it, you have to understand what Carl Sagan saw in that photograph that nobody else had been able to see in quite the same way before. Sagan was the person most responsible for the photograph existing at all. He had been arguing since the early 1980s for NASA to use Voyager 1's remaining camera capability to take a portrait of the solar system from the outside, from a vantage point that no camera had ever occupied. The idea was not primarily scientific in the narrow sense. The data value of photographing the planets from 4 billion miles was minimal. The planets would appear as points of light, not as worlds with resolvable surface features. The scientific return would be negligible compared to what the spacecraft's other instruments were still collecting. The argument for taking the photographs was not scientific. It was philosophical. It was the argument that humanity needed to see itself from outside, needed to see the Earth not as the center of everything, but as a small, fragile, improbable feature of a vast, indifferent universe, and that seeing it would change something. NASA was initially resistant. The cameras consumed power that the mission's scientific instruments needed. The pointing maneuvers required to photograph the planets would take time and engineering resources away from other mission priorities. The scientific case was weak, and for years, the bureaucratic resistance held. Sagan kept pushing. He enlisted allies. He made the philosophical case repeatedly and in writing and in conversation until the people with the authority to approve the observation were convinced that the non-scientific value was worth the non-scientific cost. The approval finally came. The command was sent. And on Valentine's Day 1990, as Voyager 1 was already moving away from the solar system on a trajectories that would carry it to interstellar space, it turned its cameras back one final time and took 60 photographs. The pale blue dot frame is the one that stopped the world. The Earth in that image occupies less than a single pixel of the photograph. It is a point of blue-white light, suspended in a ray of sunlight that scatters across the frame as an artifact of the way the camera's optics handled light from the distant sun at that extreme angle. The planet that contains every ocean, every mountain, every city, every person who has ever lived, every war ever fought, every work of art ever made, every moment of love or cruelty or brilliance or suffering in the entire history of the human species, is a mote of dust in a sunbeam, 4 billion miles from the camera that photographed it, in a solar system that is itself an unremarkable feature of an unremarkable region of a galaxy containing 400 billion stars, in a universe containing 2 trillion galaxies. That is what the photograph shows. That is what Sagan saw. And what he said about it, in a passage he wrote and later delivered as a spoken reflection, is the most important thing the space program has ever produced that is not a scientific measurement. He wrote that the Earth is a very small stage in a vast cosmic arena, that on it, everyone who ever lived, every king and peasant, every young couple in love, every mother and father, every inventor and explorer, every teacher of morals, every corrupt politician, every superstar, every supreme leader, every saint and sinner in the history of the human species, lived there on a mote of dust suspended in a sunbeam. He wrote that the Earth is the only world known to harbor life, that there is nowhere else in the foreseeable future where our species could migrate, and that, like it or not, for the moment, the Earth is where we make our stand. He wrote that our planet is a lonely speck in the great enveloping cosmic dark, and that in our obscurity, in all this vastness, there is no hint that help will come from elsewhere to save us from ourselves. It was the most honest, most humbling, most consequential thing that a photograph has ever made a human being say. And it was made possible by a spacecraft that the engineers had told to turn around one last time before its cameras went dark forever. After February 14th, 1990, the cameras were shut off. The power they consumed was needed elsewhere. The photographs they had taken were downloaded and stored and studied and eventually made available to the world, and Voyager 1 continued on its trajectory, pointed away from the sun, moving outward through the outer heliosphere toward the boundary that no human instrument had ever crossed. For the next 22 years, it sent home data from instruments that had no cameras, from a spacecraft that could no longer show humanity anything visual about the universe it was crossing, but that was still listening and measuring and recording in ways that would eventually produce discoveries more difficult to explain than anything its cameras had captured. The crossing of the heliopause in August 2012 was the moment that turned Voyager 1 from a remarkable spacecraft into something unique in the history of science. The heliopause is the boundary where the solar wind, the continuous stream of charged particles blown outward from the sun at hundreds of miles per second, is finally stopped by the pressure of the interstellar medium, the thin gas and magnetic field that fills the space between star systems. Inside the heliopause is the heliosphere, the bubble of solar influence that encompasses everything we call the solar system. Outside it is something else entirely, the interstellar medium, the material that has not been touched by our sun's direct influence, that carries the signatures of stellar explosions and the chemistry of the galaxy itself, that has been present in the space between stars for billions of years, without any of it ever being directly sampled by any instrument humanity had ever built. When Voyager 1 crossed that boundary, it crossed it with working instruments. And what those instruments recorded on the other side was not what the models had predicted. The first anomaly involved the plasma environment. Voyager 1's plasma wave science instrument, which detects oscillations in the density and motion of charged particles and converts them to audio frequency signals, recorded a dramatic increase in plasma density at and immediately after the heliopause crossing. The interstellar plasma outside the solar system was denser than the models had predicted it would be, significantly denser. The boundary region where the solar wind meets the interstellar medium was compressing material into a zone of higher density than the pre-crossing models had accounted for, and the physical mechanism driving that compression was not immediately obvious from the data. The plasma density measurement also allowed researchers to identify, for the first time ever, what the interstellar medium actually sounds like as a physical oscillation. By converting the frequency of plasma wave oscillations recorded by the instrument into audio signals, scientists produced what has been described as the hum of interstellar space, a persistent low-frequency oscillation present throughout the interstellar medium that has no equivalent in anything measured inside the heliosphere. The sound, such as it is, of the space between the stars, a physical property of the galactic environment that has existed for billions of years, present throughout the Milky Way, produced by processes operating at stellar and galactic scales, and heard for the first time by a human-built instrument that a group of engineers in Pasadena, California, pointed at the right piece of the universe and left running long enough to reach it. But the discovery that produced the most sustained and genuinely unresolved scientific discussion was not the plasma density or the interstellar hum. It was the magnetic field. When Voyager 1 crossed the heliopause, its magnetometer, the instrument that measures the strength and direction of magnetic fields in the surrounding environment, recorded the properties of the magnetic field on both sides of the boundary. Inside the heliosphere, the magnetic field is the sun's field, generated by processes in the solar interior and carried outward through the heliosphere by the solar wind. Outside the heliosphere, the magnetic field is the interstellar field, generated by entirely different processes in the wider galaxy, the accumulated magnetic influence of stellar explosions, the organized motion of galactic gas, and the large-scale structure of the Milky Way's own magnetic architecture. These two magnetic fields, solar and interstellar, were expected to be oriented differently. They are generated by completely separate physical processes. They belong to different physical systems. When two separate magnetic environments meet at a boundary, the standard expectation is a magnetic discontinuity, a clear change in a field direction that marks the physical interface between the two domains. Voyager 1's magnetometer data showed something different. The magnetic field in the region just beyond the heliopause was parallel to the magnetic field inside the heliosphere. The two fields, solar and interstellar, were aligned, not slightly similar in direction, parallel, the same orientation on both sides of the boundary that was supposed to mark the transition between them. This finding was disturbing enough when Voyager 1 alone had measured it. With only one crossing, at one location, it was possible to argue that the alignment was a local coincidence, a fortunate or unfortunate geometric accident, specific to the point in the heliosphere where Voyager 1 happened to cross. When Voyager 2 crossed the heliopause in 2018, at a completely different location 6 years later, and its magnetometer recorded the same result, that possibility was eliminated. Two spacecraft, crossing the boundary of the solar system at different locations and different times, both finding the interstellar magnetic field aligned with the solar magnetic field. The alignment is not a local coincidence. It is a property of the interaction between the sun's magnetic domain and the galaxies that the standard models had not predicted and do not have a fully satisfying explanation for. The physical implications of that alignment are significant and still being worked through in the heliospheric physics literature. If the solar magnetic field and the interstellar magnetic field are parallel at the heliopause, it means the two systems are connected in some way that goes beyond the simple picture of a bubble floating in an external medium. The heliosphere is not simply enclosed by the interstellar medium, it is magnetically coupled to it. The sun's magnetic influence and the galaxy's magnetic environment are interacting at the boundary in ways that leave a measurable signature in the field direction, a signature that no model built before the crossing predicted would be there. The discovery is real. The explanation for it is still incomplete. The data that would resolve it, more crossings at more locations with more instruments, does not currently exist and will not exist until another mission is built, launched, and travels for decades to the same region. Voyager 1's finding sits in the scientific literature, confirmed, anomalous, and waiting for the theoretical framework that will eventually account for it. The pressure waves that Voyager 1's plasma wave instrument has detected in the interstellar medium since crossing the heliopause add another layer to the picture. When the sun produces a large coronal mass ejection, a massive burst of solar plasma and magnetic field that blasts outward through the heliosphere, the disturbance eventually reaches the heliopause and sends a pressure wave into the interstellar medium beyond it. Voyager 1 has detected several of these waves since 2012, and each detection has allowed researchers to measure the plasma density at Voyager 1's location by observing the frequency at which the plasma oscillates in response to the wave. These measurements have confirmed that the plasma density in the interstellar medium has been increasing as Voyager 1 moves further from the heliopause, a result consistent with the spacecraft moving through a region of the local interstellar medium where conditions are different from the models built before any direct sampling had been done. The interstellar medium that Voyager 1 is sampling is not the average interstellar medium of the Milky Way. It is a specific region called the local interstellar cloud, a region of warm, relatively dense ionized gas that the solar system has been moving through for tens of thousands of years. The local interstellar cloud is itself embedded in a larger structure called the local bubble, a vast cavity in the interstellar medium approximately 1,000 light years across that was carved out by supernova explosions over the past 10 to 20 million years. Voyager 1 is sampling one tiny point in this specific, structured, historically shaped local environment. The data it is returning is not a characterization of the generic space between stars. It is a characterization of this particular cloud at this particular moment in the solar system's journey through the galaxy, from this particular position and direction. Every measurement is unrepeatable because the solar system is moving, and the place Voyager 1 is sampling now will not be the same place the solar system passes through in a different epoch. The spacecraft that turned around and took the pale blue dot photograph in 1990 has been moving away from that pale blue dot ever since, and the distance between them is now so great that the signal connecting them takes 23 hours to cross. In November 2026, that signal will take exactly 24 hours, one full light day, a distance that requires a different unit of measurement to even express, a distance at which the sun itself is just another star, faint and distant, indistinguishable to any eye that did not know exactly where to look. The spacecraft is still operating. Two instruments remain, the plasma wave subsystem and the magnetometer, the two instruments most directly relevant to the interstellar science that has been the mission's real contribution since 2012. Both are still working. Both are still sending home data from a place that no model built on Earth has fully accounted for. Both are still finding things that the physics built before they arrived at the boundary did not predict. The discovery that Voyager 1 cannot explain is not a single dramatic finding. It is a pattern of measurements that collectively describe a boundary, an environment, and a physical relationship between the sun's magnetic domain and the galaxies that the models built to describe them did not fully anticipate. The magnetic field alignment is unexplained. The plasma density distribution is not perfectly matched by the models. The pressure wave detections have refined the understanding of the local interstellar medium in ways that have required revisions to the theoretical picture. None of these findings has been resolved by the existing frameworks. They sit in the data, confirmed by the most distant instruments humanity has ever operated, waiting for the physics that will eventually account for them. What Voyager 1 did when it turned around in 1990 was show humanity what it looked like from outside, a pale blue dot in a sunbeam. Everything that has ever mattered to the human species on a pixel in the dark. What it has been doing since it crossed the heliopause in 2012 is show the universe what it looks like from inside the boundary between the solar system and interstellar space. And what the universe looks like from there, according to the instruments, still running on 50 watts of nuclear power in the cold, dark 15 billion miles from home, is stranger and more structurally complex and more resistant to the frameworks built to describe it than anyone who built Voyager 1 in 1977 could have predicted they were sending it to find. The spacecraft that looked back and showed us the pale blue dot is still out there. It never stopped moving. It is moving right now at 38,000 miles per hour through the interstellar medium, through the magnetic field that aligns with the sun's in ways that nobody fully understands, through the local interstellar cloud that the solar system has been traversing for millennia, sending home its measurements on a signal that takes almost a full day to arrive, from a machine the size of a small car, running on the power of a dim light bulb, built in the decade when the personal computer did not yet exist. It turned around once. It will not turn around again. But what it found when it was finally pointed back at the universe, it was entering the anomalies in the magnetic field and the plasma density and the wave behavior of the interstellar medium. That the models did not predict is a discovery that the physics of the universe has not yet finished explaining. And it came from the same spacecraft that showed us, one February morning in 1990, exactly how small the world is that built it